Welcome. The BoreCore archive is a collection of slow, methodical recordings of technical processes and perfectly boring routines designed to help you relax and fall asleep. New procedures are added regularly, so don't forget to like and subscribe. Time to relax, close your eyes, and take it on down to Sleepy Town.
Welcome to a complete operational guide to the coagulation, flocculation, sedimentation, filtration, disinfection, and distribution of municipally treated drinking water, as performed by a certified water treatment plant operator on a standard 8-hour shift. Or the reason your tap water tastes like nothing, which is the correct taste. You are a water treatment plant operator. You work at a municipal surface water treatment facility that serves a population of approximately 212,000 people. Every day, this plant processes between 20 and 30 million gallons of raw water drawn from a nearby reservoir, removing particles, pathogens, organic compounds, and other contaminants, and delivering treated water to the distribution system that carries it to homes, hospitals, schools, restaurants, and fire hydrants throughout the service area. The water that people drink, cook with, brush their teeth with, and wash their hands with passes through this plant first. This is your plant. You run it. Your certification is a Grade 4 surface water treatment operator license, which is the highest certification level for surface water treatment in your state. It required passing a series of examinations covering water chemistry, microbiology, hydraulics, filtration theory, disinfection practice, laboratory procedures, and regulatory compliance. It also required a minimum number of years of documented operating experience at progressively higher volume facilities. You passed the Grade 4 examination on your second attempt. The first attempt, 11 years ago, was close. The second attempt, 6 months later, was not close. This is the trajectory of most Grade 4 certifications. The examination is designed to be difficult. The consequences of an undertrained operator are designed not to be. Safe drinking water is one of the most significant public health achievements in human history. Before widespread municipal water treatment, waterborne diseases, including cholera, typhoid fever, dysentery, and hepatitis A, were among the leading causes of death in cities around the world. The introduction of filtration and chlorination in the early 20th century, beginning with the Jersey City, New Jersey water supply in 1908, dramatically reduced the incidence of these diseases and contributed substantially to the increase in life expectancy that characterized the 20th century. The water treatment plant you operate is the continuation of that achievement, performed daily, without ceremony, by people whose work is so successful that its beneficiaries have no reason to think about it. You find this arrangement appropriate. Your shift begins at 6 in the morning. It ends at 2:30 in the afternoon. This is the day shift, which is considered the most active shift because it overlaps with the period period of highest water demand, when the residential and commercial portions of the service area are fully operational and drawing water at peak rates. The evening and overnight shifts are quieter in terms of demand, but require the same vigilance. The plant does not have an off season. The plant does not have a day off. The plant runs continuously, staffed in rotating 8-hour shifts, every hour of every day of the year. This is a feature, not a limitation. Municipal water supply does not pause. Today is a Tuesday in early summer. The reservoir level is within normal range following a wet spring. The raw water turbidity, which is a measure of the cloudiness caused by suspended particles, is elevated slightly above the seasonal baseline from recent runoff. The temperature of the raw water is 58 degrees Fahrenheit. None of these conditions are unusual or alarming. They are the conditions you will manage today. Let us begin. You arrive at the plant at 6 in the morning and relieve the night shift operator in the control room. The handoff takes approximately 10 minutes. The night operator walks you through the current state of the plant, any adjustments made during the night, any alarms that occurred and how they were addressed, and any parameters that are trending in a direction that requires monitoring. Tonight's handoff notes are routine. Raw water turbidity has been rising since approximately 4 in the morning, consistent with the weather forecast for a rain event upstream, and the coagulant dose was increased accordingly at 4:30. Everything else is within normal operating parameters. You acknowledge the handoff, sign the operator log, and the night operator leaves. You review the overnight data on the SCADA system. SCADA stands for Supervisory Control and Data Acquisition, and it is the computer system through which you monitor and control the plant's processes. The SCADA screen shows a schematic of the entire plant with real-time data at each process point. Flow rates, chemical dosing rates, turbidity readings, pH values, chlorine residuals, pump statuses, and valve positions. The schematic is a live representation of what the plant is doing right now, updated every few seconds. You read it the way a pilot reads a cockpit instrument panel, not by examining each gauge in turn, but by taking in the whole display at once and registering any value that is outside its expected range. Nothing is outside its expected range. You note this and proceed. The source water for this plant is a surface reservoir, approximately 4 miles from the plant, fed by a watershed of approximately 90 square miles. Surface water sources are more variable in quality than groundwater sources because they are directly exposed to the environment. Precipitation events wash sediment, agricultural runoff, animal waste, and organic material into the reservoir. Seasonal algae blooms in summer can produce taste and odor compounds, and in some species, cyanotoxins. Industrial or agricultural activity upstream can introduce chemical contaminants. Natural organic matter, primarily the products of decaying vegetation, is present in virtually all surface waters and must be managed throughout the treatment process. You are aware of all of these potential influences on your source water and monitor for them continuously. The intake structure is a concrete and steel structure submerged in the reservoir at a depth of approximately 30 feet, equipped with a coarse bar screen that excludes large debris such as branches, leaves, and aquatic organisms from entering the intake pipe. The bar screen is inspected weekly and cleaned as needed. During the spring runoff period, it may accumulate significant debris and require more frequent cleaning. Raw water enters the intake through the bar screen, travels through a buried intake pipeline to the plant's low-lift pumping station, and is pumped from there to the beginning of the treatment process. The low-lift pumps run continuously, drawing water from the reservoir and delivering it to the plant at a rate that you adjust based on the distribution system's demand. Current flow rate is 22 million gallons per day, within the normal range for a Tuesday morning in early summer. You check the raw water quality data from the online monitoring instruments at the intake. Raw water turbidity is currently 4.2 nephelometric turbidity units, or NTU. This is elevated compared to the baseline of approximately 1.5 NTU during dry periods, but well within the range the plant is designed to handle. The Surface Water Treatment Rule, promulgated by the U.S. Environmental Protection Agency under the Safe Drinking Water Act, requires that finished water turbidity not exceed 1 NTU at any point in the distribution system, and sets a more stringent standard of 0.3 NTU as the target at the plant effluent. Your plant routinely produces finished water turbidity below 0.1 NTU at 4.2 NTU in the raw water. You will need to make a coagulant dose adjustment this morning. The night shift operator has already done this, but you will confirm that the adjustment is adequate. Raw water enters the plant at the rapid mix basin, which is the first stage of treatment. Before describing what happens in the rapid mix basin, it is necessary to understand why raw water is turbid and why turbidity cannot be removed by simple settling. The particles that make water turbid are a mixture of mineral particles such as clay and silt, organic particles from decaying vegetation, algae cells, bacteria, and colloidal material. Colloidal particles are particles in the size range of approximately 1 nanometer to 1 micrometer, which is small enough to remain suspended in water indefinitely without settling under gravity. The reason colloidal particles do not settle is that they carry a net negative electrical charge on their surfaces, and like charged particles repel each other, preventing them from aggregating into clusters clusters large enough to settle. If you took a jar of turbid water and simply let it stand, the larger particles would settle out over hours or days, but the colloidal fraction would remain suspended essentially forever. Coagulation is the chemical destabilization of these colloidal particles. A coagulant chemical is added to the water in the rapid mix basin and mixed vigorously with the raw water for a very short time, typically 30 to 60 seconds. The coagulant most commonly used at plants like yours is aluminum sulfate, also called alum, though ferric sulfate and ferric chloride are also widely used. The coagulant dissociates in water to release positively charged aluminum or iron ions, which are attracted to the negatively charged surfaces of the colloidal particles. These ions neutralize the charge on the particle surfaces, eliminating the repulsive force that kept the particles separated. The particles can now approach each other and begin to aggregate. This process of charge neutralization is coagulation. Flocculation follows coagulation. After charge neutralization in the rapid mix basin, the water passes into the flocculation basin, where it is mixed gently and slowly over a period of 20 to 30 minutes. The gentle mixing creates contact between the destabilized particles, allowing them to collide and stick together, forming progressively larger aggregates called floc. The floc particles grow from individual colloidal particles, invisible to the naked eye, into visible masses the size of snowflakes, and ultimately into settling size aggregates that can be removed by sedimentation. The flocculation basin has a series of paddle mixers that rotate slowly, creating the gentle, rolling turbulence needed for particle contact without the shear forces that would break apart the forming floc. The correct mixing intensity is measured by the velocity gradient, designated g, typically expressed in units of seconds to the -1. Too high a g value breaks the floc. Too low a g value produces insufficient contact between particles. The correct range for the flocculation stage at your plant is 15 to 40 seconds to the -1. You verify the paddle mixer settings. They are correct. The coagulant dose is the most important variable in the coagulation process. Too little coagulant fails to neutralize the particle charges completely, leaving residual turbidity in the water. Too much coagulant produces a positive charge on the particle surfaces, which also causes repulsion and results in a phenomenon called charge reversal, which also produces poor turbidity removal. The correct dose is the minimum dose that achieves complete charge neutralization, which varies with the raw water turbidity, the type and concentration of particles present, the water temperature, and the water pH. At lower water temperatures, the coagulation chemistry is slower, and a higher dose or longer contact time may be needed. At higher turbidity, more coagulant is required simply because there are more particle surfaces to neutralize. The current coagulant dose, set by the night operator at 4:30 this morning in response to the rising turbidity, is 22 milligrams per liter of alum, measured as the concentration in the raw water after mixing. You verify this against the jar test results from the night shift. The night operator conducted jar tests, which are bench scale simulations of the coagulation and flocculation process using small jars of raw water and varying doses of coagulant to determine the optimal dose. The jar test at 22 milligrams per liter produced the best floc formation and the lowest settled water turbidity. You confirm the dose is set correctly on the chemical feed pump. The pump is delivering the correct flow rate of coagulant solution. The dose is 22 milligrams per liter. This is consistent with your experience for a raw water turbidity of 4.2 NTU at this water temperature. Water from the flocculation basin flows into the sedimentation basins. Your plant has 4 sedimentation basins operating in parallel, each approximately 150 feet long, 60 feet wide, and 14 feet deep. The sedimentation basins are large, open, rectangular tanks of concrete, covered with a roof to prevent wind disturbance and algae growth. They look from the outside like large rectangular buildings with no windows. Inside, the water moves very slowly. Sedimentation works on a simple physical principle. Particles denser than water will sink if given sufficient time and calm conditions. The key parameter is the overflow rate, also called the surface loading rate, which is the flow rate divided by the surface area of the basin. At a lower overflow rate, water spends more time in the basin and particles have more time to settle. Your plant's sedimentation basins operate at a design overflow rate of approximately 500 gallons per day per square foot of basin surface area, which is a typical value for conventional sedimentation following alum coagulation. The floc particles that have formed in the flocculation stage settle through the water column. As they travel horizontally through the sedimentation basin, the water enters at one end and exits at the far end over a series of submerged weirs, which are low barriers that the clarified water must flow over on its way to the next treatment stage. The settled solids accumulate at the bottom of the basin as a thick slurry called sludge. The sludge must be removed periodically to prevent it from resuspending and degrading the settled water quality. You inspect the sedimentation basins during your morning rounds. Each basin has a sludge collection system, a series of mechanical scrapers that travel along the bottom of the basin on a slow, continuous cycle, pushing the accumulated sludge toward a hopper at the inlet end of the basin, from which it is pumped to the solids handling system. You verify that the sludge scrapers in all 4 basins are operating. Basin 2's scraper shows a slightly elevated drive motor current on the SCADA display, which can indicate increased sludge loading or a mechanical resistance in the scraper chain. You walk to Basin 2 and listen to the scraper drive unit. The sound is normal, no unusual grinding or straining. The elevated current is consistent with the increased sludge load from the higher raw water turbidity this morning. You note it and continue monitoring. You observe the settled water quality at the outlet end of each basin. You collect a sample of settled water from Basin 3 and measure its turbidity with the portable turbidimeter you carry during rounds. The reading is 0.8 NTU. This is slightly higher than the 0.5 NTU you typically see from the settled water at this time of year, which reflects the elevated raw water turbidity this morning and the somewhat reduced settling efficiency that results from colder water temperatures. 0.8 NTU is acceptable for settled water and well within the range that the filters downstream can handle reliably. Filters are designed to work best when the turbidity of the water they receive is below about 2 NTU. Your settled water at 0.8 is giving the filters good conditions to operate in. Settled water turbidity above 2 NTU typically indicates a coagulation problem. Insufficient or excessive coagulant dose, inadequate mixing, or a raw water quality change that the current chemical program has not yet adjusted for. The appropriate response is to conduct additional jar tests and adjust the coagulant dose. Your settled water is at 0.8. The coagulation is working adequately. You note the value in the operator log and continue. The sludge pumped from the sedimentation basins is sent to the solids handling system. At your plant, the solids handling system consists of gravity thickeners, which concentrate the dilute sludge by allowing additional water to separate, and a belt filter press, which squeezes the thickened sludge into a semi-solid cake suitable for land application or landfill disposal. The sludge from alum coagulation is primarily aluminum hydroxide, and the settled particles removed from the raw water. It is not hazardous waste. It is a mildly alkaline slurry that, when properly handled and tested to confirm it meets land application standards, can be applied to agricultural or disturbed lands as a soil amendment. The sludge handling and disposal is managed by the solids handling operator, a separate position from yours. You are aware of the system's operation and will respond if it has problems. But its day-to-day management is not your primary responsibility today. Settled water from the sedimentation basins flows by gravity to the filter building, which contains 8 dual media gravity filters operating in parallel. Filtration is the removal of particles that escaped the sedimentation process, including small flock particles, algae cells, and any particulate matter that was not adequately settled It is also the primary treatment barrier for Giardia and Cryptosporidium, two protozoan parasites that are resistant to chlorine disinfection at normal doses, and that must be physically removed by filtration to meet regulatory requirements. Each filter is a rectangular basin, approximately 20 feet by 30 feet, filled with filter media through which the water passes downward by gravity. Your filters use a dual media configuration: 18 inches of anthracite coal on top of 12 inches of silica sand, supported on a gravel underdrain system. The anthracite, which is a dense, hard coal with particles ranging from 1 to 2 millimeters in size, forms the upper layer and captures the larger flock particles. The sand below, with particles averaging 0.5 millimeters, provides finer filtration and polishes the water. The dual media design allows the larger particles to be captured in the anthracite before they can blind the finer sand, and allows the filter to operate at a higher flow rate before requiring backwash than a single media sand filter would. The mechanism by which filtration removes particles is not simply physical straining, as many people imagine. A particle of 1 micrometer diameter could pass easily through the spaces between even the finest sand grains. The actual removal mechanism is a combination of interception, sedimentation, diffusion, and most importantly, attachment. Particles flowing through the filter media contact the surfaces of the media grains and adhere to them. The attachment is driven by the same van der Waals forces and charge interactions that influence colloidal particle behavior in the coagulation step. A filter that has been properly conditioned with a correct coagulant dose in the water entering, it will have media surfaces that are chemically favorable for particle attachment. A filter receiving poorly coagulated water will have less favorable attachment conditions and will produce poorer effluent quality. The coagulation step and the filtration step are therefore chemically connected, and problems in coagulation manifest as problems in filtration. You check the filter effluent turbidity for each filter. The continuous online turbidimeters on each filter effluent line display the current readings on the SCADA. Filter 1, 0.08 NTU, filter 2, 0.09 NTU, filter 3, 0.11 NTU, filter 4, 0.07 NTU, filter 5, 0.13 NTU, filter 6, 0.08 NTU, filter 7, 0.09 NTU, filter 8, 0.12 NTU. All filters are producing effluent well below the regulatory limit of 0.3 NTU, filter 5. At 0.13 NTU, has the highest effluent turbidity of the group, but is still more than twice as good as the regulatory limit. You note filter 5's slightly elevated value and check its operational history on the SCADA. Filter 5 completed a backwash cycle at 3 this morning and has been in service for approximately 3 hours since the backwash ended. Its turbidity is tracking the normal ripening curve. Immediately after backwash, filter effluent turbidity is initially elevated as the clean filter media begins to accumulate a conditioning layer of particles, then decreases to its best performance level as the filter matures, then slowly increases again as particle loading on the media increases toward the backwash trigger point. 3 hours post-backwash is within the normal ripening period. You note this and continue. Filter run length, the duration a filter operates before requiring backwash, is a key operational metric. Longer filter runs indicate efficient filtration and lower backwash water usage, which is desirable. Very short filter runs can indicate a coagulation problem, sending too much particulate to the filters, a raw water quality event, or a media condition problem. Your plant's filters typically run between 20 and 40 hours before reaching the backwash trigger, which is set at a filter effluent turbidity of 0.2 NTU, or a head loss of 8 feet. Head loss is the pressure drop across the filter as particles accumulate in the media, and it is the other common trigger for backwash. As the filter loads with particles, the resistance to flow increases, requiring more pressure to maintain the same flow rate. You check the head loss values for all 8 filters. Most are in the range of 2 to 4 feet of head loss, well below the backwash trigger of 8 feet. Filter 7 is at 5.8 feet of head loss, which is approaching the trigger point. Filter 7 has been in service for 31 hours. You note that filter 7 will likely require backwash sometime this afternoon. You add this to your mental operating schedule for the day and note it in the operator log. At 9 in the morning, filter 6 reaches its backwash trigger. The online turbidimeter shows a reading of 0.21 NTU, slightly above the trigger threshold of 0.2 NTU. This is expected. Filter 6 has been running for 28 hours and was due for backwash within the next several hours. You initiate the backwash sequence for filter 6 from the SCADA control panel. Filter backwash is the process of cleaning a loaded filter by reversing the flow of water through the media, expanding the media bed, and flushing the accumulated particles out of the filter. The backwash water flows upward through the filter at a high enough velocity to fluidize the media, which means the media grains become suspended in the water, rather than resting against each other, allowing the accumulated particles between the grains to be washed free and carried out of the filter by the upflowing water. The backwash water, which is highly turbid with the removed solids, flows over a trough at the top of the filter and is directed to the plant's backwash recovery system. The backwash sequence at your plant is a 4-stage automated process controlled by the SCADA system. Stage 1 is the air scour, which precedes the water wash. Compressed air is introduced from the under-drain system at the base of the filter, rising through the media in large bubbles that scour the surfaces of the media grains and break apart the particle deposits that have become compacted in the media. The air scour lasts approximately 3 minutes. You can see the surface of the filter media heaving and churning as the air escapes upward through it. The surface looks like a slowly boiling material, which is an accurate description of what it is. Stage 2 is the simultaneous air and water wash, which begins after the air scour. Water is introduced from the underdrain at a rate sufficient to begin fluidizing the media while the air scour continues. This combination of air and water washing is more effective at cleaning media than water washing alone, particularly for removing the biologically active slime that builds up on media grains over many filter runs. The simultaneous wash lasts approximately 4 minutes. Stage 3 is the water-only wash, in which the air is shut off and the backwash water flow rate is increased to fully fluidize the media and wash the loosened particles upward and out of the filter. This stage requires careful attention to the backwash flow rate. Too low a flow rate does not fully fluidize the media and leaves particles trapped in the bed. Too high a flow rate washes the media itself out of the filter into the backwash waste troughs. The correct backwash flow rate for your dual media filters is approximately 15 gallons per minute per square foot of filter area, which expands the anthracite layer approximately 40% and the sand layer approximately 20% above their resting depths. This degree of expansion ensures complete fluidization and thorough cleaning without media loss. You monitor the backwash flow rate on the SCADA throughout this stage. Stage 4 is the rinse, a period of continued water flow at a reduced rate after the main backwash wash is complete. The rinse settles the fluidized media back into stratified layers and clears any remaining turbidity from the filter box before the filter is returned to service. After the rinse, the filter is refilled with settled water from above the filter to displace the rinse water, and the filter is returned to the normal downward filtration mode. The entire backwash cycle takes approximately 15 minutes from initiation to the return of the filter to service. During this period, the filter is not producing treated water, and the other 7 filters in service carry the full plant flow. The plant's design allows any one filter to be taken out of service for backwash without exceeding the combined filtration capacity of the remaining filters. Backwash water usage, the volume of treated water used to clean the filters, is approximately 1 to 2% of the plant's total production. This water is recovered in the backwash recovery basin, allowed to settle, and returned to the head of the plant for retreatment. Recovering backwash water reduces water loss and the plant's impact on the watershed. The recovered water is blended back with raw water at a rate that does not exceed 10% of the total raw water flow to prevent the accumulation of problematic concentrations of any contaminants in the recycle stream. Filter 6's backwash completes at 9:17. The filter is returned to service. The initial post-backwash turbidity on filter 6 is 0.18 NTU, consistent with the normal ripening phase. It will decrease to below 0.1 NTU within the next hour as the filter matures. You note the backwash completion in the operator log. Filter 6 backwash completed 9:17. Duration 15 minutes. Post-backwash turbidity 0.18 NTU. Returned to service. This entry is part of the required record keeping under the filter backwash recycling rule, a federal regulation that mandates documentation of all filter backwash events and recycling operations. You recorded correctly. Filtered water from the 8 filters flows by gravity into the clearwell, which is a large, covered underground storage reservoir beneath the plant. Before entering the clearwell, the filtered water passes through the disinfection contact chamber, where the primary disinfectant is added and allowed to react with the water for a controlled period of time. Disinfection is the treatment step that kills or inactivates pathogenic microorganisms, including bacteria, viruses, and protozoa, rendering the water microbiologically safe to drink. The disinfectant used at your plant is free chlorine, added as sodium hypochlorite solution. Sodium hypochlorite is the same chemical compound as household bleach, though at a different concentration. Household bleach is approximately 5% sodium hypochlorite, while the bulk sodium hypochlorite used at water treatment plants is typically 12.5 to 15%. The sodium hypochlorite solution is delivered to the plant in tank trucks and stored in a chemical containment area adjacent to the plant. It is fed from the storage tanks to the disinfection contact chamber by metering pumps, which dose it at a precisely controlled rate based on the flow rate of the filtered water and the target chlorine residual. When sodium hypochlorite is added to water, it reacts with water to form hypochlorous acid and hypochlorite ion, which together are called free chlorine. Hypochlorous acid is the more biologically active form. It penetrates the cell walls of microorganisms and disrupts their metabolic processes, inactivating them. The relative proportion of hypochlorous acid to hypochlorite ion in water depends on the pH. At lower pH values, hypochlorous acid predominates, and the disinfectant is more effective. At higher pH values, hypochlorite ion predominates, and the disinfectant is less effective. This pH dependence is one reason that maintaining the correct water pH throughout treatment is important for disinfection efficiency. The effectiveness of chlorine disinfection is quantified by the CT concept, where C is the chlorine concentration in milligrams per liter, and T is the contact time in minutes. The product C times T equals the CT value, expressed in milligram minutes per liter, which is proportional to the degree of inactivation achieved. The U.S. Environmental Protection Agency has published CT tables that specify the CT values required to achieve specific log inactivation credits for Giardia and viruses under different conditions of temperature and pH. Your plant is required to achieve 3 log inactivation of Giardia, meaning a 99.9% reduction in the Giardia concentration, and 4 log inactivation of viruses, meaning a 99.99% reduction. The CT required to achieve these credits depends on the water temperature and pH. At your current conditions, a water temperature of 58 degrees Fahrenheit and a pH of 7.2, the CT required for 3 log Giardia inactivation is approximately 195 milligram minutes per liter. The contact chamber at your plant has a design contact time, called the T10, of 40 minutes at peak flow rate. T10 is the time by which 10% of the water has passed through the contact chamber, and it is used rather than the average hydraulic retention time because it represents the fastest moving water in the chamber. Using T10 ensures that even the fastest moving portion of the flow receives adequate contact time. At 40 minutes T10 and your current chlorine residual of 2.4 milligrams per liter entering the contact chamber, the CT value is 2.4 times 40, which equals 96 milligram minutes per liter. This is less than the required 195. You make up the remaining CT requirement with ultraviolet light disinfection, which is your plant's secondary disinfection barrier. The ultraviolet UV disinfection system is located downstream of the chlorine contact chamber. UV light at wavelengths of 250 to 270 nanometers is absorbed by the DNA of microorganisms, causing photochemical damage that prevents replication. UV disinfection is particularly effective against Cryptosporidium, the protozoan parasite that is highly resistant to chlorine. The UV system at your plant is designed to deliver a dose of 40 millijoules per square centimeter at peak flow rates, which achieves more than 3 log inactivation of Cryptosporidium. The combined CT from the chlorine contact chamber and the UV dose from the UV system together provide the required inactivation credits for all target pathogens under your current operating conditions. You check the UV system status on the SCADA. All 6 UV reactors are online and running. Reactor 3 shows a lamp intensity reading of 92% of nominal, compared to the other reactors in the range of 95 to 98%. The lamps in the UV reactors degrade gradually over time, losing intensity as they accumulate operating hours. When a lamp's output falls below 80% of nominal, it should be replaced. Reactor 3, at 92%, is within the acceptable operating range, but trending toward the replacement threshold. You note this in the operator log and add a task to the maintenance schedule. Inspect Reactor 3 lamps at next scheduled maintenance, projected for next week. After the disinfection contact chamber and the UV system, the treated water undergoes several additional chemical adjustments before entering the clear well. These adjustments address characteristics of the water that are not pathogens, but that affect the water's safety, aesthetic quality, or its behavior in the distribution system. The first adjustment is pH correction. Water that has been treated with alum coagulant typically has a reduced pH. Because the coagulation reaction consumes alkalinity, the water's natural buffering capacity. Low alkalinity water is corrosive to metal pipes and fixtures in the distribution system, which can lead to elevated concentrations of lead and copper in the water at consumers' taps from the leaching of pipe materials. The lead and copper rule, a federal regulation under the Safe Drinking Water Act, requires water systems to control the corrosivity of their water to prevent this leaching. Your plant adds hydrated lime, calcium hydroxide, to the treated water after the clear well to raise the pH and increase the alkalinity. The target pH at the plant effluent is 7.8, and the target alkalinity is 40 milligrams per liter as calcium carbonate. These targets are set based on the Langelier saturation index, a calculation that predicts whether water of given chemistry will tend to deposit a thin protective calcium carbonate scale on pipe surfaces, which is the preferred condition for corrosion control. The Langelier saturation index, LSI, is calculated from the water's pH, temperature, calcium concentration, alkalinity, and total dissolved solids concentration. An LSI of 0 indicates the water is in equilibrium with calcium carbonate and will neither deposit scale nor dissolve it. A slightly positive LSI in the range of 0 to 0.5 indicates the water is slightly supersaturated with calcium carbonate and will deposit a thin protective scale. This is the target condition for corrosion control in distribution systems with metal pipes. You calculate the LSI daily using the current water chemistry data and adjust the lime feed to maintain the LSI in the target range. This morning's calculated LSI is 0.18, which is within the target range. No lime dose adjustment is needed. The second adjustment is the addition of orthophosphate, a corrosion inhibitor used in systems with lead or copper service lines. Orthophosphate reacts with lead and copper at pipe surfaces to form insoluble mineral scales. specifically lead phosphate and copper phosphate, which coat the interior of the pipes and reduce the rate at which lead and copper leach into the water. Your distribution system has a legacy population of older homes, some with lead service lines from the era before the 1986 lead pipe ban, and some with copper plumbing soldered with lead-based solder. Orthophosphate addition has been a component of your corrosion control program since 2012, when lead monitoring data indicated that lead levels at some customer taps were approaching the action level of 15 micrograms per liter. Since the orthophosphate program was implemented, 95th percentile lead levels in monitoring data have decreased by approximately 70%. The program works. You add it. The third adjustment is fluoridation. Your water system adds fluoride to the treated water to maintain a concentration of 0.7 milligrams per liter in the distribution system, which is the current recommendation of the U.S. Public Health Service for optimal dental health benefit. The fluoride source is fluorosilicic acid, a byproduct of phosphate fertilizer manufacturing that is commercially available in bulk at appropriate purity for water treatment use. The fluorosilicic acid solution is metered into the treated water by a dedicated chemical feed pump at a rate calibrated to maintain the target concentration. You verify the fluoride concentration in the treated water by measuring a sample in the laboratory using the SPA-DNS method, a colorimetric test that produces a color in proportion to the fluoride concentration and is read on a spectrophotometer. The laboratory result is 0.68 milligrams per liter, slightly below the target of 0.7. You increase the fluoride feed pump rate by a small increment and note the adjustment. You will retest in 2 hours to confirm the adjustment has brought the concentration to the target. The fourth and final chemical addition before the clear well is the application of a secondary chlorine dose. The primary chlorine was added at the disinfection contact chamber to provide the inactivation credit. The secondary chlorine, also called a chloramine in systems that use combined chlorine, is added to maintain a disinfectant residual throughout the distribution system. Federal regulations require that a detectable disinfectant residual, defined as a free chlorine residual of at least 0.2 milligrams per liter, or a combined chlorine residual of at least 0.5 milligrams per liter, be maintained at all points in the distribution system. Your plant uses free chlorine throughout, and the target residual leaving the plant is 1.8 to 2.2 milligrams per liter, which is sufficient to maintain detectable residual at the far ends of the distribution system, after accounting for the chlorine demand of the water in the pipes during transit. Treated water flows from the chemical adjustment point into the clear well. The clear well is a covered, underground storage reservoir with a capacity of 8 million gallons, approximately a third of the plant's daily production. The clear well serves two functions. The first is operational buffering. It stores treated water that can supply the distribution system during periods when production temporarily falls below demand, such as during a filter backwash event or a brief equipment outage. The second is contact time. The residence time of water in the clear well contributes to the total CT for the chlorine disinfection process, supplementing the contact chamber's contribution. The clear well is not a passive tank. Water enters at one end and exits at the other, flowing in a baffled pattern that maximizes the residence time by preventing short-circuiting, which is the tendency of water to flow in a direct path from inlet to outlet without using the full volume of the tank. Baffles are walls within the clear well that extend from the floor to near the ceiling, forcing the water to travel back and forth across the full width of the tank before reaching the outlet. The baffling efficiency of the clear well has been verified by a tracer test, in which a known concentration of a tracer chemical, typically fluoride or lithium chloride, was added to the water entering the clear well, and its appearance at the outlet was monitored over time to characterize the flow pattern. The T10 for your clear well at current flow rates is approximately 220 minutes, meaning the fastest moving water spends at least 220 minutes in the clear well. This is a significant contact time contribution. Water exits the clear well through the high service pumps, which are the large centrifugal pumps that pressurize the distribution system. Your plant has 5 high service pumps, each with a capacity of approximately 5 million gallons per day, providing significant redundancy. Even with 2 pumps out of service, the remaining 3 can meet the plant's design production capacity. The pumps run continuously, their speed adjusted by variable frequency drives in response to the distribution system pressure monitored at key points throughout the service area. When distribution system pressure drops, indicating that demand has increased or that a large water main break has occurred, the pumps automatically increase their speed to maintain the target pressure. When pressure rises, indicating lower demand, the pumps slow. You check the distribution system pressure readings on the SCADA. The system shows pressure monitoring points at 7 locations throughout the service area, ranging from a high-pressure zone near the plant at 82 pounds per square inch to a low-pressure zone at the far eastern end of the service area at 58 pounds per square inch. The minimum acceptable distribution system pressure is 35 pounds per square inch under normal conditions, which ensures that water is delivered at adequate pressure to multi-story buildings and to meet fire flow requirements. All monitored points are within normal pressure ranges. The pump stations in the distribution system. There are 3 booster pump stations that serve elevated portions of the service area are all operating normally. The distribution system also includes storage tanks, elevated tanks, and ground-level reservoirs distributed throughout the service area that supplement the plant's production during peak demand periods. Your service area has 4 elevated storage tanks with a combined capacity of 6 million gallons. These tanks fill overnight when demand is low and draw down during the high-demand morning period when residential and commercial usage peaks. You monitor the tank levels on the SCADA throughout the shift, watching for any unusual depletion that might indicate a distribution main break. Tank levels this morning are at 72 to 81% of capacity, within the normal range for this time of day. A significant portion of your shift is devoted to water quality monitoring and laboratory analysis. The Safe Drinking Water Act and its associated regulations require extensive testing of both the treated water and the distribution system water at specified frequencies using specified methods, with results reported to the State Drinking Water Program on a defined schedule. This monitoring is not optional, and it is not abbreviated during busy operational periods. The monitoring is part of running the plant, not ancillary to it. You collect the morning composite sample from the plant effluent. A composite sample is a sample made up of smaller subsamples collected at regular intervals throughout the sampling period and combined in proportion to the flow at the time of each subsample collection. Composite sampling produces a sample that represents the average water quality over the entire sampling period, rather than a snapshot at a single moment. For regulated parameters that are measured as daily averages, composite sampling is more representative than grab sampling. You collect a subsample from the plant effluent sampler every 2 hours and add it to the composite container in proportion to the flow. The composite container is refrigerated to preserve the sample. At the end of the 24-hour sampling period, the composite sample is sent to the laboratory for analysis of disinfection byproducts and other regulated parameters. Disinfection byproducts, DBPS, are chemical compounds formed when disinfectants, such as chlorine, react with natural organic matter in the water. The 2 primary classes of regulated disinfection byproducts are trihalomethanes, THMS, and halocetic acids, HAS. Trihalomethanes include chloroform, bromidichloromethane, dibromochloramethane, and bromoform, all of which are formed when chlorine reacts with organic precursors derived from decaying vegetation. Halocetic acids are a group of 5 compounds formed in similar reactions. Both THMS and HAS are potential human carcinogens at elevated concentrations, and the EPA has established maximum contaminant levels of 80 micrograms per liter for total THMS and 60 micrograms per liter for 5 HAs, measured as running annual averages. Your plant's historical THM levels have been well below the regulatory limit, typically in the range of 25 to 40 micrograms per liter. Because your source water has relatively low organic precursor concentrations, and because your treatment process removes a significant fraction of the precursors before chlorination, managing disinfection byproduct formation is a balance between the need for adequate disinfection, which requires chlorine, and the goal of minimizing byproduct formation, which requires limiting chlorine contact with organic matter. The conventional approach is to remove as much natural organic matter as possible before chlorination, which is one reason that the coagulation, flocculation, sedimentation, and filtration steps are so important. They remove not only turbidity-causing particles, but also dissolved organic matter through adsorption onto the floc particles. Enhanced coagulation, a practice encouraged by the DBP regulations, uses a higher coagulant dose, specifically to achieve better removal of dissolved organic matter, accepting some operational penalty, such as increased sludge generation, in exchange for lower DBP formation potential. Your plant practices enhanced coagulation during periods of high organic matter loading in the raw water, which typically occurs following spring runoff. You conduct the mid-morning laboratory testing in the on-site laboratory. You measure the turbidity of the finished water using a bench turbidimeter, 0.06 NTU, which is an excellent result. You measure the free chlorine residual of the finished water using the DPD colorimetric method, in which a small tablet of N,N-diethylphenylenidiamine, DPD, is dissolved in a sample of the water, and the resulting pink color is read on a spectrophotometer, with the color intensity proportional to the chlorine concentration. The result is 1.92 milligrams per liter, within your target range of 1.8 to 2.2. You measure the pH of the finished water using a calibrated pH meter, 7.78, close to the target of 7.8. You measure the temperature, 62 degrees Fahrenheit. The treated water is slightly warmer than the raw water at 58 degrees, which is expected. The water absorbs a small amount of heat as it flows through the above-ground portions of the treatment process. You measure the alkalinity using a titration method and calculate the Langelier saturation index. The LSI is 0.21, within the target range. You record all measurements in the laboratory logbook, which is a bound, numbered logbook with no erasable entries. All laboratory data is recorded in ink, and errors are struck through with a single line and initialed rather than obliterated. This is the same standard that applies to the operator log. The integrity of the data record is as important as the data itself. You also conduct the daily fluoride verification test, following the fluoride feed pump adjustment you made earlier. The result is 0.71 milligrams per liter, which is at the target of 0.7, and confirms that the dose adjustment was appropriate. You note the confirmation in the log. At noon, you conduct the daily distribution system chlorine residual monitoring. The surface water treatment rule requires water systems to maintain a detectable disinfectant residual throughout the distribution system and to monitor residuals at a minimum number of locations each day. Your system has 42 designated monitoring locations distributed throughout the service area at a mix of near plant, mid-system, and far-reach locations. Each day, a subset of these locations is sampled and the chlorine residual is measured. The sampling rotation covers all 42 locations over the course of a week. Today's sampling route covers 8 locations in the northern portion of the service area. You drive the route in the plant's sampling vehicle, a van equipped with a portable water quality testing kit. At each sampling location, which is typically a fire hydrant, a low-flow sampling tap installed by the water system, or a business that has agreed to allow regular sampling access. You flush the sample point for a standard duration before collecting the sample. Flushing removes the water that has been standing in the service connection and ensures that the sample represents the water in the main rather than stagnant standing water, which may have depleted chlorine residual and does not represent distribution system water quality. You measure the chlorine residual at each location using the same DPD colorimetric method used in the laboratory, adapted to a portable photometer small enough to use in the field. You also measure the pH and temperature at each location. The results from today's sampling at the 8 northern locations range from 0.42 milligrams per liter at the far northeast end of the service area to 1.18 milligrams per liter at a mid-system location. The minimum result of 0.42 is well above the regulatory minimum of 0.2 milligrams per liter. The spatial pattern of decreasing chlorine residual with increasing distance from the plant is expected and normal. Chlorine is consumed by its reaction with organic matter and biofilms in the distribution pipe network as the water travels further from the plant. One location on today's route, a sampling tap near a large industrial customer at the northwest corner of the service area, shows a result of 0.31 milligrams per liter, which is lower than the historical range of 0.5 to 0.7 milligrams per liter for that location. A lower than usual residual at a specific location can indicate several things. Increased water age at that location due to reduced demand, a change in the pipe network that has altered the flow path, or an increase in chlorine demand from a new source. You note the low result and flag it for follow-up. You will resample this location tomorrow and compare the results. If the result is consistently lower than historical, you will investigate the possible causes. One low result in isolation is an observation. Two consecutive low results are a trend requiring investigation. You also collect bacteriological samples at 2 locations on today's route. Total coliform bacteria monitoring is required under the total coliform rule, which specifies how many distribution system samples must be taken monthly. What constitutes a positive result, and what follow-up actions are required when positive results are found. Total coliforms are a group of bacteria that includes both harmless environmental organisms and the fecal indicator organism, Escherichia coli. The presence of total coliforms in a distribution system sample indicates a potential pathway for contamination. Though it does not necessarily mean the water is immediately unsafe to drink. The presence of E. coli specifically indicates fecal contamination and is a more serious finding that requires immediate investigation and notification. Your system has had no E. coli positive results in the distribution system in the last 7 years. You collect the bacteriological samples in sterile sample bottles containing sodium thiosulfate, which neutralizes any residual chlorine in the sample and prevents it from continuing to kill bacteria after the sample is collected, and you place them in an ice chest for transport to the certified laboratory that performs the bacteriological analysis. The laboratory results will be available tomorrow. At 12:30, the SCADA alarm panel indicates a high turbidity alarm on filter 2. The filter effluent turbidimeter is reading 0.23 NTU. Above the alarm threshold of 0.2 NTU, you respond to the alarm. A high turbidity alarm on a filter can have several causes, and the correct response depends on identifying the cause before taking action. You examine the trend data for filter 2 on the SCADA. The turbidity has been increasing gradually over the past 40 minutes, which is not a sudden spike, but a slow rise. Sudden spikes in filter effluent turbidity typically indicate a mechanical problem with the filter, such as a cracked under drain or a breach in the filter media. Gradual increases typically indicate that the filter is approaching the end of its run and needs backwash, or that the quality of the settled water entering the filter has changed. You check filter 2's operational history. Filter 2 has been running for 22 hours since its last backwash. 22 hours is within the normal run length range. You check the head loss on filter 2, 5.2 feet, which is approaching, but not yet at the backwash trigger of 8 feet. The head loss is not the reason for the high turbidity. You then check the settled water turbidity entering the filters. It has increased from 0.8 NTU at your morning rounds measurement to 1.1 NTU now. The raw water turbidity has also increased from 4.2 NTU this morning to 5.8 NTU currently. The rising raw water turbidity, consistent with the ongoing runoff event upstream, has caused the settled water turbidity to increase, and the filters are responding to the increase in loading with a corresponding increase in effluent turbidity. The primary corrective action is to increase the coagulant dose to address the higher raw water turbidity. You conduct a rapid jar test in the on-site laboratory, testing raw water samples at 22, 25, and 28 milligrams per liter of alum. The jar test results show that at 25 milligrams per liter, the settled water turbidity improves to 0.6 NTU, which is better than the current 1.1 NTU. At 28 milligrams per liter, the result is similar to 25, suggesting that 25 is near the optimal dose for the current conditions. You increase the coagulant feed pump to deliver 25 milligrams per liter, and note the change in the operator log with the time. The raw water turbidity that prompted the change, the jar test results, and the new dose. The effect of the dose increase will take approximately 30 to 45 minutes to propagate through the coagulation, flocculation, and sedimentation processes and reach the filters. During this period, filter 2 continues to show elevated turbidity. You do not backwash filter 2 immediately, because backwashing a filter that is operating within acceptable performance does not address the root cause, which is the inadequate coagulant dose. After the new coagulant dose has propagated to the filters and the settled water turbidity has improved, the filter effluent turbidity should improve as well. If filter 2's turbidity does not decrease after the coagulant adjustment takes effect, you will then consider whether to backwash it or investigate other causes. At 1:15, approximately 45 minutes after the coagulant dose increase, the settled water turbidity in the SCADA has decreased to 0.62 NTU, and filter 2's effluent turbidity has decreased to 0.14 NTU, below the alarm threshold. The alarm clears. The coagulant adjustment was the correct response. You note the resolution in the operator log. Filter 2 high turbidity alarm resolved following coagulant dose increase from 22 to 25 milligrams per liter. Filter 2 effluent turbidity decreased from 0.23 to 0.14 NTU. Alarm cleared at 13:15. This documentation is thorough for a reason. When your state's drinking water program reviews your operational logs as part of a sanitary survey, the record of how you responded to the alarm is evidence of competent operation. A log that shows an alarm occurred and cleared with no notation of the cause, the investigation, and the corrective action is a log that tells the regulator Nothing except that the alarm system works. A log that shows the full diagnostic and response sequence tells the regulator that the operator understands the plant and can manage it when it does not behave as expected. You document thoroughly. This is a professional habit and a regulatory expectation simultaneously. The afternoon portion of your shift is partly occupied by regulatory compliance documentation. Water treatment plants are among the most heavily regulated facilities in the country, subject to federal rules under the Safe Drinking Water Act, state regulations that are at least as stringent as the federal rules, and any additional local requirements. The monitoring, reporting, and record-keeping requirements of these regulations generate a substantial documentation burden that is part of the job, not separate from it. The primary federal regulations that govern your plant's operation include the Surface Water Treatment Rule and its revisions, which establish treatment technique requirements for turbidity, Giardia inactivation, and virus inactivation, the Stage 2 disinfectants and disinfection byproducts rule, which sets maximum contaminant levels for THMS and HAS, and specifies the monitoring protocol, the Total Coliform Rule, which governs bacteriological monitoring, the Lead and Copper Rule, which requires corrosion control treatment and monitoring at customer taps, the Groundwater Rule, which applies to systems using groundwater sources and does not apply to your surface water plant, but which you should understand because your service area includes a small groundwater source used for supplemental supply, and the Unregulated Contaminant Monitoring Rule, which requires periodic monitoring for a list of contaminants that are not yet regulated but are candidates for future regulation. The Consumer Confidence Report, or CCR, is an annual report that all public water systems are required to deliver to their customers, describing the source water, the treatment process, the regulated contaminants detected in the previous year's monitoring, and a plain language explanation of any violations and what the system has done or is doing to correct them. Your system mails the report to all residential customers and posts it on the utility's website. Preparing the CCR is a task that falls to the water quality manager, not to you directly, but you contribute the operational data that populates it and review the draft for technical accuracy before it is published. The CCR for the previous year showed no violations of any drinking water standard, which is the goal and the normal result for a well-operated system. It also showed that all regulated contaminants were detected at concentrations well below their maximum contaminant levels. The report is, in a literal sense, the public record of how this plant has been run. You complete the daily operational report for submission to the State Drinking Water Program's online reporting system. This report includes the total volume of water treated today, the maximum and average finished water turbidity, the maximum and minimum chlorine residuals at the plant. And at the distribution system's farthest monitoring point, the log inactivation credits achieved for Giardia and Cryptosporidium. The chemical doses applied the filter operational data, including run lengths and backwash events, and a certification signed by you as the responsible operator that all data is accurate and that the plant was operated in compliance with all applicable regulations during the reporting period. The certification is a legal attestation, providing false information in a report to the State Drinking Water Program is a violation of both state and federal law, with penalties including substantial fines, and for repeated or willful violations, criminal prosecution. You sign the certification because the data is accurate, because the plant was operated in compliance, and because signing an accurate certification is an unremarkable part of a normal operational day. You sign it with the same matter-of-fact attention you bring to every other task in the shift. This is not heroism. It is professional practice. In the final hour of your shift, you address 2 items from the preventive maintenance schedule. Preventive maintenance is the systematic program of inspections, lubrications, calibrations, adjustments, and replacements performed on equipment at specified intervals to prevent failures before they occur. It is a less glamorous aspect of plant operation than process management, but it is the reason that the high-service pumps, the chemical feed pumps, the filter backwash systems, and the other mechanical and electrical components of the plant continue to function reliably year after year. The first maintenance item is the monthly calibration of the online turbodimeters. Online turbodimeters are instruments mounted in the process flow at multiple points throughout the plant, continuously measuring the turbidity of the water passing through them and sending the readings to the SCADA. They are the most operationally important instruments in the plant because their readings drive the coagulant dose adjustments, the filter backwash decisions, and the regulatory compliance monitoring. An online turbodimeter that is reading incorrectly is a turbodimeter that is misleading the operator and potentially masking a water quality problem. Regular calibration ensures they remain accurate. Turbodimeter calibration uses primary standards, certified suspensions of known turbidity value that are traceable to the National Institute of Standards and Technology, NIST. You use a 0 NTU standard, which is particle-free water that should read 0 on the instrument, to verify the instrument's 0 point, and a secondary standard of known NTU value to verify its response across the measurement range. If the instrument reads outside a specified tolerance from the standard values, the calibration is adjusted. If the instrument cannot be adjusted to within tolerance, it is flagged for service or replacement. You calibrate the turbodimeter on filter 4's effluent line. The 0 standard reads 0.0 0.01 NTU, which is within the acceptable tolerance of plus or minus 0.02 NTU, the secondary standard. A certified 1 NTU standard reads 1.03 NTU, which is within the acceptable tolerance of plus or minus 5%. The turbidimeter is in calibration and requires no adjustment. You record the calibration in the instrument calibration log. Instrument ID, date, standards used, standard values, measured values, technician initials, result. In calibration, no adjustment required. You move to the next filter and repeat. You calibrate all 8 filter effluent turbidimeters and the raw water turbidimeter. All are in calibration. The second maintenance item is the weekly inspection of the chemical containment area. Chemical storage and handling at water treatment plants is subject to both drinking water regulations and chemical safety regulations, including the EPA's Risk Management Program for facilities storing large quantities of hazardous chemicals. Your plant stores sodium hypochlorite in quantities that trigger Risk Management Program requirements. The storage tanks hold approximately 10,000 gallons total, and sodium hypochlorite at the concentration used in water treatment, approximately 12.5%, is classified as a hazardous substance at these quantities due to its corrosive and oxidizing properties. The containment area inspection verifies the condition of the secondary containment, the bermed or walled area surrounding the chemical tanks that would capture a spill and prevent it from reaching the environment. The integrity of the tank walls and fittings, checked visually for signs of leakage, corrosion, or damage. The functioning of the ventilation system in the chemical building, which removes chlorine gas that off-gases from the sodium hypochlorite solution. The condition of the emergency eyewash and safety shower stations, and the availability and condition of the personal protective equipment stored in the chemical area for emergency response use. The inspection is uneventful. The containment area is clean and dry, indicating no leakage from the tanks or piping. The ventilation system is operating, confirmed by the airflow indicator on the fan housing. The emergency eyewash stations are activated briefly to verify that they flow and that the water runs clear. The PPE, which includes chemical-resistant gloves, face shields, chemical-resistant aprons, and self-contained breathing apparatus, SCBA, is in its designated location in good condition and within its inspection date. The sodium hypochlorite tanks show levels consistent with the daily usage records. The combined tank level has decreased by approximately the expected volume based on yesterday's feed pump records. No discrepancies are noted. You record the inspection as satisfactory. A complete description of water plant operation would be incomplete without a discussion of emergency response, even though your day-to-day has not required it. Water treatment plants are required by the America's Water Infrastructure Act of 2018 to conduct risk and resilience assessments and to maintain emergency response plans. The Emergency Response Plan is a documented, regularly updated plan that specifies how the system will respond to a range of emergency scenarios. Natural disasters, infrastructure failures, cybersecurity incidents, and contamination events. A water main break in the distribution system is the most frequently occurring emergency event for most water systems. Your system responds to main breaks by isolating the affected section of main using the valve network, rerouting flow through alternate pathways, and dispatching repair crews. During a main break, distribution system pressure may drop in the affected area, and a boil water notice may be required if the pressure drops below the minimum required to prevent backflow of contaminated groundwater into the distribution main. A boil water notice advises customers to boil water before consumption until the system is repaired, flushed, and tested to confirm the absence of bacteriological contamination. Your system has issued 2 boil water notices in the past 11 years. One following a significant main break in 2017, and one following a pump station failure in 2020. Both were resolved and rescinded within 48 hours. A source water contamination event is a more serious scenario. If a significant contamination event occurs in the watershed or in the reservoir, the plant may need to curtail withdrawals and rely on stored clearwell and distribution system storage while the contamination passes or is addressed. For certain contaminants, particularly some industrial spills, the plant may be capable of treating contaminated water with supplemental activated carbon or other treatment modifications. For others, the only response is to cease withdrawals until the source water quality returns to acceptable levels. Your plant maintains an emergency interconnection with a neighboring water system, which can provide limited supplemental supply during source water events. The interconnection has been tested annually as part of the Emergency Response Plan exercises. It has not been used in an actual emergency in the past 11 years. A cybersecurity incident at a water treatment plant is a scenario that has become more relevant in recent years as plant control systems have become more networked. In 2021, an attacker remotely accessed the SCADA system of a water treatment plant in Oldsmar, Florida, and briefly increased the sodium hydroxide dose to an extremely high level, which was detected and corrected by the operator before the water reached the distribution system. This event prompted the water sector to increase its focus on cybersecurity for operational technology systems. Your plant has implemented network segmentation between the business network and the operational control network, multi-factor authentication for SCADA access, and enhanced monitoring for unusual system activity. You also have the ability to operate all critical plant processes manually without reliance on the SCADA as a contingency for a complete system compromise. The manual operating procedures are documented and you are trained in their use. You hope never to use them. You are trained in their use regardless. Chemical feed failures are perhaps the most operationally frequent emergency scenario, and they range from a minor pump malfunction to a complete loss of disinfectant addition. A loss of chlorine feed is the most serious chemical failure because it means the primary disinfection barrier is not functioning. Your plant's response to a chlorine feed failure is to switch to a backup feed system, a redundant chemical feed pump on a parallel line that can take over immediately when the primary pump fails. If both primary and backup feed systems fail, the plant is required by regulation to notify the state drinking water program immediately and to take corrective action within a specified time period. In practice, the backup system has successfully covered every primary pump failure in your tenure at the plant. At 2 in the afternoon, the afternoon shift operator arrives for the 2:30 handoff. You begin preparing the handoff summary. The handoff is the most critical communication event of the operating day because it is the moment at which operational responsibility transfers from one operator to another. And any information not communicated in the handoff is information the incoming operator does not have when they need it. You walk the incoming operator through the current plant status. Raw water turbidity is 5.8 NTU and has been rising since early this morning, consistent with runoff from recent rainfall. Coagulant dose was increased from 22 to 25 milligrams per liter at 12:30, following a filter 2 high turbidity alarm, and a jar test confirming the higher dose is appropriate filter 2 alarm resolved at 13:15 all filters, currently within normal operating parameters. Filter 7 head loss at 6.1 feet and will require backwash within the next 4 to 8 hours UV. Reactor 3 lamp intensity at 92% of nominal within acceptable range, but noted for maintenance review next week. Fluoride feed adjusted upward at 10:30 following a low laboratory reading. Retest at 12:30 confirmed 0.71 milligrams per liter. No further adjustment needed. Distribution system. Chlorine residuals within normal range at all monitored locations, except the Northwest Industrial Sampling Tap at 0.31 milligrams per liter lower than historical range, flagged for resampling tomorrow. Bacteriological samples collected and sent to laboratory results. Expected tomorrow. All regulatory reports completed and submitted for today. The incoming operator reviews the day's log entries while you narrate the handoff. They ask one question: what was the settled water turbidity when the coagulant dose increase was made at 12:30. You tell them 1.1 NTU at the time of the alarm, decreased to 0.62 NTU after the dose increase propagated to the filters. They nod. This is the kind of detail that matters during a handoff. Not just what was done, but the conditions that prompted it and the conditions that confirmed its effectiveness. You sign the operator log as the departing day shift operator at 14:22. The incoming operator signs as the arriving afternoon shift operator. Responsibility has transferred. The plant is in competent hands. You are no longer the responsible operator. You remove your coveralls in the equipment room, wash your hands, and change into your street clothes. You drive home. The plant continues operating. It operated before you arrived this morning. It will operate after you leave this afternoon. It will operate tonight while you sleep, staffed by the evening shift operator who arrived at 2:30 and will be relieved at 11 by the night shift operator. The plant does not know you have left. The water does not know you have left. The 212,000 people who will turn on their taps this evening and tomorrow morning do not know you were here. The water will taste like nothing. This is the correct taste for water that has been correctly treated. You made it that way today, as you do every day you work this shift. The next shift operator will make it that way tonight. The operator after them will make it that way tomorrow. The chain does not break because no individual in it allows it to break. You are one link in that chain. You have done your part. You have completed a day shift at a municipal surface water treatment plant. During this shift, you reviewed the overnight data and conducted a shift handoff, checked the raw water quality, and confirmed the coagulant dose was appropriate for the current conditions, conducted morning rounds of the sedimentation basins, and filters with turbidity measurements and visual inspections, initiated a filter backwash on filter 6, and documented the event, verified the disinfection system's performance and compliance with the CT requirements, adjusted the fluoride feed to maintain the target concentration, calibrated all 8 filter effluent turbidimeters and the raw water turbidimeter, responded to a high turbidity alarm on filter 2 by conducting a jar test, and increasing the coagulant dose, conducted the distribution system, monitoring route covering 8 sampling locations, collected bacteriological samples for laboratory analysis, completed the daily operational report, and submitted it to the state drinking water program, inspected the chemical containment area, noted the UV reactor 3 lamp intensity for maintenance follow-up, prepared, and delivered the shift handoff to the incoming afternoon operator. The plant produced approximately 11 million gallons of treated water during your 8-hour shift, which is roughly half of today's projected total production. That 11 million gallons traveled from the reservoir to the intake, through the low-lift pumps, through coagulation and flocculation, through sedimentation, through filtration, through disinfection, through pH adjustment, through orthophosphate addition, through fluoridation, through secondary chlorination, into the clear well, through the high service pumps, and into a distribution system of approximately 600 miles of water main, eventually arriving at approximately 80,000 service connections, where it was available for use the moment a tap was opened. The person who poured a glass of water this morning and drank it without thinking about it received water that was treated by this process, managed today by you, managed yesterday by someone else, managed every day for decades by a succession of certified operators who kept the same standard without variation, because the standard does not vary when it is the standard that keeps people safe. Waterborne disease in the United States is not a historical relic. It is an ongoing threat that is controlled by ongoing treatment. In developing countries without equivalent water treatment infrastructure, diarrheal diseases from contaminated water kill approximately 1.5 million children under the age of 5 every year. In the United States, the combination of source water protection, treatment, distribution system integrity, and monitoring has reduced the death toll from waterborne disease to a fraction of what it was a century ago. The water treatment plant is not the only element of this protection, but it is the central one. It runs every day. It is staffed by people who understand what they are doing and why it matters. You are one of those people. You arrived this morning at 6. You left at 2:30. You will be back on Thursday. Good night. The afternoon shift operator has adjusted the coagulant dose to 26 milligrams per liter. The raw water turbidity reached 6.4 NTU at 3 in the afternoon. The plant is responding correctly. The water will taste like nothing tomorrow morning. This is correct.